Okay, so this is the first section in Chapter 5 in the textbook. It's using fundamental identities. So with trigonometric functions, we have certain identities, so certain relationships that we can use to describe others. So if I go through this, which hopefully looks somewhat familiar, I'll go through this one at a time. We have what's called the reciprocal identities. And the reciprocal identities should look somewhat familiar. So sine of any value u is equal to 1 over the cosecant of u. And this makes sense because this notation shows that it's a reciprocal, thus the reciprocal identity. So if we remember that the sine of theta is equal to 1/2, then the cosecant of theta must be equal to 2, showing that these are reciprocals. Or, that really the cosecant of theta is equal to 1 over 2, which is 1 over the sine of theta. So that's all these reciprocal identities are. So we can write tangent as 1 over the cotangent, much in the same way we can write them as just reciprocals of each other. Next up, we have the quotient identities. So yet again, hopefully seem familiar. If we remember that sine is y over, if sine is y and cosine is x, then the tangent is y over x. So we can just write y over x as sine over cosine. Same thing with cotangent. Cotangent is x over y, so that's cosine over sine. So that's all these are. So these identities, these first 8, hopefully are simple enough to grasp. There's not a whole lot of new memorization to happen here because we've been working with these already. Now the other identities that become somewhat more challenging are called the Pythagorean identities. Pythagorean identities follow the Pythagorean theorem. So a squared plus b squared equals c squared. In the last unit, we used this to find the radius of for our trigonometric functions. Well, if we remember that, yet again, referring back to cosine is x and sine is y, in the unit circle, the radius is 1. So here we'd have sine squared of u plus cosine squared of u is equal to radius squared, which is 1. And so that's how we get this first identity. Now we can use the same reasoning as well to get these other two identities. So tangent being sine over cosine, or y over x, secant 1 over x. But for all this, we don't want to take up the time to prove these identities. We're more focused on using them. So you will need to memorize all these. Again, these first 8 you should already know, you should be familiar with. These last 3 are the ones that may pose a little bit of a challenge. But as long as you know a squared plus b squared equals c squared, you pretty much already know this first one. And then notice that these last 2 are pretty similar. So tangent and cotangent are reciprocals. Secant and cosecant are reciprocals. So yet again, a little bit of similarities there. Now, we use them for instances such as this. So this is a problem we've seen before. But if I know that the secant is negative 3 over 2, I want to find the values of all 6 trigonometric functions. So sine of theta, cosine of theta, tangent of theta, cosecant of theta, secant, and cotangent. The secant is negative 3 over 2, so we know that the cosine is going to be negative 2 over 3. They are reciprocals of one another. Don't forget that cosine is x over r, so this is x over r. Because sine is y over r, we know that now the radius is 3. So we just need to find the y value, and we do that by x squared plus y squared equals r squared. Yeah. Secant, yep. So here, if x is negative 2, plus we want to find y is equal to 3 squared. So y squared is equal to 9 minus 4, so y is equal to the square root of 5. Now here's the key thing. Tangent is positive. So if the tangent is positive, that means that tangent is y divided by x, so that's sine divided by cosine. So if this is going to be positive, look at what we have here. We have a positive divided by negative. The way this is written out, it should be a negative. So we need to make this sign negative. And one of the reasons we can just make it a negative is actually right over here. Because we take the square root of 5, remember y is going to be a plus or minus. So we can only take one of those values, and this tells us which one. So this tells us we need to have that negative. So tangent is going to be sine of theta over cosine of theta. So that is negative root 5 over 3 divided by negative 2 over 3. And 3's cancel out, so we get root 5 over 3. And then over here, we're going to have 3 root 5 over 5 after flipping this and then reducing the radical. And then over here, this is going to be a negative 3 root 5 over 5. Oh, sorry, that should be a 2. These should all be 2's. Okay, so that's all better. So using these identities, we can get that. But we can also use our identities for stuff like this. Here we have a trigonometric expression, sine of x times cosine squared of x minus sine of x. And we want to simplify this. We want to make this look better. So what we do is we refer back to our identities and we see, well, what can we use? There's, a lot going on here, but then we see this. Sine squared plus cosine squared equals 1. So if I know that sine squared of x plus cosine squared of x is equal to 1, that means that cosine squared of x is equal to 1 minus sine squared of x. So I can substitute this in. I can say, all right, I get sine of x times 1 minus sine squared of x minus sine of x. Let's distribute this in. So we get sine of x minus sine cubed of x minus sine of x. Well, rearranging this, I can see I have a sine of x minus a sine of x. No matter what that is, I'm subtracting it from itself, so that cancels out, and I'm left with negative sine cubed of x. Notice, in the original, we had to plug in x 3 times into the same expression. Now we only need to do it once. Thus, it is simplified. So that's how we can use our identities. So here are some more examples. Here are some more problems. So the trick here and the key is trying to view the patterns. So whenever you see something squared, most of the time, not always, but most of the time, it's probably one of those Pythagorean identities. So here I see 1 plus cotangent squared. And that's actually one of my identities, 1 plus cotangent squared. So I can replace 1 plus cotangent squared with cosecant squared. Well, sine of theta is just 1 over cosecant. So, so I can make this 1 over cosecant of theta times cosecant squared of theta over 1. So I get cosecant squared of theta over cosecant of theta, which would just be cosecant of theta. Much in the same way, if I have x squared over 1 times 1 over x, they cancel out. The square and the singular cancel out. See how it's simplified? We can do the same approach over here. So sine squared of theta, I know that sine squared of theta, well, I know sine squared of theta plus cosine squared of theta is equal to 1. So look at how this is 1 minus sine squared of theta. So I can get cosine squared of theta is equal to 1 minus sine squared of theta. 1 minus sine squared of theta, 1 minus sine squared of theta. So this is cosine squared of theta over sine squared of theta. And if I compare these two, cosine over sine, well, cosine over sine is cotangent. And because these are both squared, this gives me cotangent squared of theta. And I'm done. Number 3, I have cosine and cosecant. So I'm just going to work in the numerator first, and I'm going to replace the cosecant with 1 over sine. So that gives me cosine of theta over sine of theta over tangent of theta, which is divided by tangent of theta. Well, cosine of theta over sine of theta, that's the same as cotangent of theta. So I have cotangent of theta divided by tangent of theta, or times 1 over tangent of theta. 1 over the tangent of theta, though, is cotangent theta. So I have cotangent theta times cotangent theta. So that's cotangent squared of theta. Simplified. And then finally here, cosecant squared of alpha minus cotangent squared of alpha. So we get those cosecant cotangents. We can use one of these Pythagorean identities. So here, cosecant squared is equal to 1 plus cotangent squared. So I'm going to replace this cosecant squared with 1 plus cotangent squared of alpha minus cotangent squared of alpha. And then just by doing that substitution, I have this last term there. They cancel out. I'm left with just 1. So no matter what alpha is, this will always be 1. So those are your identities, and that's them in action. From my experience, this is very difficult for a lot of people because it involves a lot of substitution where you don't always know exactly what you're substituting. So for these problems here, you have to kind of look and see what can you plug in to make this really simple. You know, with this fraction in number 3, how can you simplify this? How can you reduce this down so we can clean it up a bit? So it does take time, it does take practice. So make sure you put in good effort on your homework, and we'll be doing lots of practice in class.